Hello students, I hope that you are good, well and fine. Today we will be starting this chapter number 5, continuity and differentiability. In this today's session we will be specifically talking about continuity. What do we mean by continuity? What is its definition, continuity in an interval, geometric meaning and points of discontinuity. We will be seeing all of these things. So let's jump to our first thing, the introduction part, or what do we actually mean by continuity. Okay, so let me just skip the introduction. This is not so much of it. Okay, so the main thing is to what is the definition. Okay, or let me just give you the some things. As continuity means that the graph would look like a continuous function. Means what? No breaks, there will be no breaks, no holes. Okay, the line tracing the function never jumps from one point to another, and there are no gaps or missing pieces in the graph. That's it, if you talk about in layman languages. Okay, so for example, this is continuous, nice continuous as this point 2. So you have nice continuous or tracing your graph without lifting your pen. Okay, this is nice intro, the example of continuous function. Okay, here discontinuous function, as you can see. Yes, so here you have to lift your pen to make the graph further. Now again lift your pen to make the graph, again lift your pen to make the graph. This is continuous. So these points where we are having jumps, we will be calling it as points of discontinuity. Okay, points of discontinuity. Clear? Okay, now let us move to the next. Now comes the definition. The main thing is the definition. In mathematics, the main thing is definition. So suppose f is a real function. Real function means domain and codomain both coming from reals. Okay, on a subset of real numbers, and let C be a point in the domain of f. So this means the C must be from the domain. Okay, this point you must have to memorize, that this C will be from domain of f. Okay, then f is continuous at C. That means we are talking about continuity at a point. Okay, we are talking about continuity at a point. This is the definition for point continuity or continuity at a point. Okay, a function is continuous at a point. We are talking about at a point. Okay, at a point. And that point must belongs to, first of all, that point must belongs to the domain. You cannot talk about out of the domain. Okay, you cannot talk about out of the domain. Cannot talk about points out of domain. Okay, you are prohibited, you are restricted to only talk about points which is in the domain. Okay, so this means then f is continuous if this limit, this my function is whatever given to me, fx, and this c is from its domain, then x approaches to c, then its limit is f of c, the actual point, sorry, the actual output of the function at point c. If this limit is equal to that thing, then you can say your function is continuous at that point. Okay, we are talking about at a point. And this x tends to c means we are approaching from the left also, we are approaching from the right also. Okay, for example, suppose you have a graph like this function. Okay, now this is your what, f of, this is c, this is your f of c point, this is your what, f of c, and what this limits shows you, x tends to c of f of x. This means when you are approaching from the right hand side, left hand side, and you are approaching from the right hand side to c, you are approaching from right to left, right side to c, and left side to c, to both side, and you came across that this limit is going to be what, f of c, then you say that your function is continuous at that point which is c. Okay, clear? Okay, so more elaborately, if the left hand and a right hand limit of the value of the function at C exist and equal to each other, then f is said to be continuous at xc. Okay, we are talking about continuity at a point. Please do make this point clear that we are talking about continuity at a point. Okay, now next, for example, you all know fx is this given to you, so you have to check the continuity. So quite simple, this is a equation of a line, or you can say, and then, or if you try to see the x tends to 1, then your limit, your fx3 will be what? Fx3 will be this thing, which is what? Which is 5, which is the value of f of 1. So your limit and your actual value all equal to each other. This means it is continuous function. By graph you can also look at it like this. Your graph will be x is 0, then y is 3, y is 0, then x to be what? 3 by 2. Yes, minus 3 by 2, x to be minus 3 by 2. So your graph will be like this, I think. Okay, clear? Okay. Okay, now again we have to examine the continuity at x is equals to 0. So fx is this, so limit x tends to 0 of f of x will be, or fx is just x square, this means 0 square, this means 0, and this is just nothing, f of 0. So your function is continuous, and its graph, if you try to see, is like this. Yes, at 0, f of this will be your f of 0, which is 0, and if you are approaching from the you are approaching 0 from the left hand side and from the right hand side, you will be seeing that x square value is also approaching to the 0, and this is also approaching to the 0. Okay, clear? Okay, let us move to the next. Now again we have to discuss the continuity of modulus function at x is equals to 0. So limit x tends to 0, you all know that mod of x. Okay, and you know that mod x is what? X, if x is greater than equals to 0, if x is negative, then minus 0. So this means I have to break it. So this means this will be break into two parts. One is left hand side limit and another is right hand side limit. Right hand side limit showed by this positive sign, and left hand side showed by this negative sign. Okay, now this will be, if we are approaching from the negative side, means left hand side, left hand side means negative side means x will be negative. The what function we will be using? We will be using this. So this means minus of x, this means minus of 0, this means just 0, and here we will be using x, this means 0, this means just 0. In both cases, what you are getting? 0, 0, and which is equals to f of 0. F of 0 is 0. So this means left hand, right hand, and the actual value all are equal to each other. This means this function is continuous at 0. If you try to see it by graph, so this will happen. This is what happening. So if you approach to the right, the function value is also going towards 0, as you can see. But here you will be using x, and this, if you are coming from the left hand side, this value, function value, is also coming to the 0, but you are using minus of x, and the actual value is 0, f of 0. Okay, that's why it is continuous. By graph you can also visualize or see it. Okay. Okay, now here again we have to show that it is not continuous. Okay, let's see. F of 0, the actual value is 1, as you can see, f of 0 is 1, but the limit f of x tends to 0 will be what? X cube plus 3, and this will be what? Just 3, as you can see, 0 cube plus 3, this means just 3. Yes, this means just 3. So this means that limit x tends to 0, you are getting this 3, and but the actual value is 1, so 1 is not equals to 3. So you can see that it is discontinuous at 0. It is discontinuous at 0. Not continuous means discontinuous. Okay, clear? Okay, I hope that the continuity concept is now getting clearer. If not, then no problem. We will be discussing more and more and more example. Okay, let us move next. Now we have to check the points where the constant function is continuous. Very simple. You all know constant function. Say it is a, this is k, then your f of k value will be this. Yes, it is defined on whole R. Okay, so limit, pick any c, pick if c belongs to the domain. Obviously we are talking about domain is R. If c belongs to any real number, then x tends to c, f of x value will be what? Limit x tends to c k, and this will be just fixed, which is k, and this is what? F of c value is also k. So this means left and right hand side and the actual value all are same. This means my function is continuous. Okay, my function is continuous. I hope that it is clear. Okay, now let us move next. Here we have to prove the identity function on real numbers. Okay, identity function on real numbers given by this is a continuous at every real number. Okay, this means pick if c belongs to any real number. C must be in domain. You always know that c must be in the domain. Domain is whole real number R. So this means, first of all, f of c will be what? F of c will be just c. Okay, limit x tends to c, f of x will be what? Limit x tends to c, f of x will be, limit x tends to c, this thing, and this will be just c, and this is just nothing but f of c. So your limit and the actual value coincides. Whenever this happens, coincides. Whenever the value coincides, this means your function is continuous at every real number. Not every, that your function is continuous at this point c, and c can be anything. So this means your function is continuous on every point of real number. Okay, or every point from the domain. Okay, and if you try to see from the graph looks like this, line passing through the origin. Okay, line passing through origin. As you can see, line passing through origin, fx is equals to x. As you can see, this is a continuous graph. Simple, easy things. Okay, let us move to next. Now, continuity in an interval. Now, so far we have talked about continuity at a point. Continuity at a point, which says that if c belongs to domain of f, this point must be clear that we always take a point from the domain. We would be not talking about outside the domain. So domain of f, then okay, continuity at a point means if c belongs to the domain of f and limit x tends to c, f of x is same as f of c, then we say then the given function, the function f is continuous at the point c. Clear? We talked about continuity at a point. Now we will be seeing continuity in an interval. Okay, so the definition is quite simple. If f is said to be a continuous in an open interval, okay, open interval, which means a comma b, if it is continuous at every point in this interval. So f, now the domain is what? A comma b, open interval a comma b, and the points are what? These all numbers in between a and b, excluding a and b. So if my function is continuous at every point inside this interval, okay, then I will say my function is continuous in an this open interval. Okay. Now, what about closed interval? The only thing differ is here that the my function must be continuous at every point inside every point inside this interval, and also that this thing also happen that limit x tends to a, but from the right hand side you all know that close interval ab on the real line will be like this. Yes, like this. We showed that it is my function is continuous inside it. This is the only domain. Okay, this is the domain. This means the continuity only works when we are talking about domain. Okay, then a is also in the domain. So how we check the continuity at this point a? So quite simple. We only can verify the continuity if we approach a from the right hand side. Can you approach from the left hand side? No. Why? Because domain these value, the value from the left hand side, if we approach from the left hand side, these value are not in the domain. The values which are in the domain is a, and the values which are right side of a. Yes, so that's why we only talk about the right hand side limit at a and the left hand side limit at b, as you can only approach towards b from the left hand side. Okay, then this must be equal to f of a, then this left hand side must be equals to f of b. If these all three things happen, then you say that your function f is continuous in the closed interval. Okay, I hope that it is clear. We are always talking about what? We are always talking about the points which are in domain. We are not getting out of the domain. That's why we took x. We are approaching a from the right hand side, and we are approaching b from the left hand side. Only from the one direction, not two directions. Okay, clear? Okay, so you can take analogy like this, that you are walking and you face a wall. Okay, then you know if you are here, then you can move this direction, you can move in this direction. Yes, but if you are standing just here, just touching the wall, then you cannot move further, you cannot move. Yes, the only direction you are going to move is this direction only. So that's what it is written in this mathematical language, that what direction we have, what direction we can choose. If we have to move towards a, we have to move towards a. Yes, you cannot move from this direction because this is not your domain. This is not. The domain is this. So that's why you can only have this direction to approach towards A and this direction as approach towards B. Okay, clear? Okay, and now let us move next. Now geometrical meaning, f will be a continuous at x equals to c if there is no break in the graph of the function at the point c. We are talking specifically, we are talking about at point c. We are specifically talking about at point c. What this means? If you have a function, okay, like this, and here you have like this, okay, and suppose, let me just fx. Geometrical meaning means fx is defined like this way: x is equals to, if x is positive and x is negative, then it will be what you can say 2x. Okay, so this means what is happening, that x is 0. This means your graph looks like what? Or you can say just this thing, x minus x. Then this will be what? Your graph will be, this is your just modulus function. So your graph will be like this. Okay. Now as you can see, if you talk about this point 0, we have no break. We have no break. As you can see, no break. No break means continuous at the point C. Okay, so far so good. Now suppose, now we defined our function x is equals to x for x greater than, strictly greater than 0, and this we do not define. The domain is this, just the domain is this. Now your function will be what? Your function will be like this. Yes, your function graph will be like this. Okay, is this continuous or not? If you try to look at using this graph, then you can see the whole, but it is continuous. Why? Because the graph says about x when x is equals to c, and that c must be from domain. That c must be from domain. Here 0 is not from domain, so it is continuous. Okay, so we only talk about domain things. If you are having some jump, if you are having some hole, then please verify that that point, the where we are having jump, is contained in domain or not. If it is contained domain, then it is discontinuous. If it is not contained in domain, then it is continuous. Okay, clear? So second, and in interval, function is said to be continuous. There is no break in the graph of the function in the entire interval. Okay, if we talk about in the interval, suppose this is my interval and your graph is this, then it is continuous. If suppose in this interval, so my domain is this whole thing. If you face any hole, any loop, any break, any other thing, this means this is discontinuous. Sorry, not continuous. Or now we will be say not continuous. Okay, clear? This will be not continuous. I hope that it is clear. What do we mean by continuous? I have given you quite examples that will be helpful to you, that when we say it is continuous and not continuous. So whenever you have such thing happening, please verify that what, first of all, the what point it is, and then the point, is that point belongs to the domain or not. If it does not belongs to the domain, then it will be continuous. For example, this is continuous. Why? Because 0 doesn't belong into the domain. Okay. Now let us move to next. Now discontinuity, quite simple. If f will be discontinuous at x is equals to a in any of the following cases. First, that limit of approaching x tends to a from the left hand side and the limit of x tends to a approaching from the right hand side exist but not equal, then you can say if the left hand side limit and the right hand side limit exist, okay, if they exist but are not equal to this point f of a, then discontinuous. Okay, and the second thing is that f of a, and second thing is that f of a is not defined. F of a is not defined, then you will also say that it is discontinuous. Okay, clear? I hope that it is clear. What do we mean by discontinuous? Okay, so clear? Now let us move to next. Now in this example, we have to find the value of the constant k so that the function f defined below is continuous at 0. So we have to find that where this function will be 0. So f of 0 is k. This means this will be same as limit of x tends to 0 where x minus this thing will happen. Where x minus this thing will happen. Okay, so quite simple. What we will do, so you all know that 1 minus cos theta limit x tends to 0 is what? You all know that. Okay, so x tends to 0, 1 minus cos theta, you all know also. Let me just draw graph for it so that you will have easy to find that what is happening. Okay, now you know the graph like this. Okay, graph like this. Now what is happening, quite simple, that we have 1 minus cos x. If you try to draw this graph, okay, this did what? Just nothing. So just observe that what about this cos x? What about this cos x? If limit x tends to 0, if limit x tends to 0, then what will happen to this? You all know this is going to 1. You all know that it is going to be 1. Okay. Now what? Now you have, okay, so this means the limit x tends to 0, cos of x is going to be 0. Okay. So far so good. Now, one thing is very clear by the graph. If you try to see that that what is happening is quite clear. Okay, what is happening is quite clear that this, if you approach towards 0, then your graph of cos x will be like this. Your graph of cos x will be like this. Yes? Yes or not? Now, from this, what you can say is quite simple, quite easy. That you have limit x tends to 0, 1 minus cos x will behave, as you can see, will behave like what? As you can see, will behave like minus of x square. Okay, will behave like this thing, as you can see. Sorry, just x square will behave like x square. Why I'm saying that? Let us see. So this is cos x, this is just cos x graph. Now minus cos x graph will be, if let me just see in this interval, then minus cos x graph. So I did what? Just did minus thing. So you will have minus cos x. So this will be 0 minus 1. So this graph is for minus of cos x. This graph is for minus of cos x. Okay, so far so good. Now what I did, I added 1. Now your graph will be shifted upwards. So your graph will be like this. As you can see, this is what your 1 minus cos x graph. As you can see, your graph behaves like parabola. Your graph behaves like parabola. This means you will have this. And what? From where I have this information? If you try to see, if you remember the cos x expansion. Okay, cos x expansion. From that, okay, from that we get this. Okay, so don't worry, you will be seeing the expansions. Okay, now what? So far so good. You will have, as you can see, okay, so this means this will happen. 1 minus cos x will be behave like x square. So this means as you move further, so you are having what? This thing. This means limit, or in other words, what you can say is that, okay, so you also know that one thing is very clear. What? 1 minus cos, if you remember what, that cos 2 theta is 1 minus cos, okay, 1 minus 2 sine square theta. Yes, so this means if theta is equals to 2x, then cos of 4x, will be 1 minus 2 sine square what, 2x. Yes, so from here what you can say, I can replace. So this will be 2 times of sine square 2x. Yes or not? This will be 2 times of sine square 2x. Okay, and in denominator we have this, so this will get cancelled. You will have 4 times of x square, and this will be 2x whole square, and this will be this thing. Yes, this will be this thing. And what you know, you know that limit of sine x divided by x, if x tends to 0, is 1. Yes, if x tends to 0 is 1. Okay, so this means 1 square. So it will be, we are just using limit properties, and this will be just nothing but 1 square, which is 1. So this means k must be 1. This means k must be 1. Okay, this means k must be 1. Okay, I hope that it is clear to you by using this information just. Okay, so we use this identity. What if we use try to evaluate using this concept also, that it is x square. Okay, then what will happen? This is for what? Just x. What if we talked about 4x? Okay, oh, we are having 4x. Yes, we are having 4x. Okay, so it will be what? Your 4x square, something like this. Yes. Okay, so this means you will have uh, okay, clear? I hope that it is clear to you. Okay, so I think we please do not try this. Okay, I think I'm making some error. Okay, okay, but the approach is very different, very unique in itself. So please think about this approach. But I think I'm getting the something out of the box or out of the lane. Okay, so please do prefer this step, the where we use the identity matrix. Okay, I hope that it is clear. We sorted things, as you can see. Okay, so let me just once again go through it. So we used what? 1 minus sine 2 theta. This will be what? Just 2 times of 2x. Okay, so this will be just nothing but we use this information. So this will be 2 sine square this thing. Okay, so this will be 2 sine square 2x. Okay, now we already have what? We already have so this will be 2 sine square 2x divided by x 8 square. This will be just 4. So 4 will be 2x whole square. This means sine 2x by 2x is going to be 0 whenever this happens. So you have just 1. So your value for k will be just 1. Okay, so that's it for now. I hope that you understood this example. Okay, so don't worry if you didn't understood. So we will make it clear next time. Okay, we will be having more questions on this continuity topic and with more problems using limits. Okay, so thank you all for now. That's it. Okay, so we will be back with more examples and more theoretical part of this continuity and differentiability chapter 5. So again, thank you.